All right, in this last one I gave you a solved problem that has a lot of rounding to get it to where I've only given you, 2 decimals in there. But because of that, I have A, B, and C are largish quantities, and then D is in parts per million. So it's a mixture of 4 components, and then the total flow rates are given. And I asked you to do some very specific checks. So I asked you whether this satisfies a total material balance on the overall system. So the overall system, first of all. Overall system is this whole thing. So it's as if I'm ignoring that those are 2 separate pieces of equipment there. And so what I have is streams 1, 2, and 4 coming in, and streams 5 and 6 coming out. So if I want to check the total material balance, that's looking at the total flow rates. So in, I had 80 and 40 and 50. And out, I have 50 and 120. And this says that 170 equals 170. So yes, indeed, this checks. So yes, the total material balance on the overall system is satisfied. Okay. The second part here says, does stream 1 satisfy the equation that the sum of x's equals 1.0? So what that's saying is add up the compositions of all the components in stream 1. So I have 0.70 plus 0.30 plus 0.00 plus 120 times 10 to the minus 6 parts per million. Okay, and this becomes 1.000120. Okay, now these numbers here were only given to 2 decimal places. So I can only take these first 2, so therefore this is indeed 1.00 to the significant figures that are given. So yes, this satisfies the equation. Chances are very good that this was really 0.699993, or something teeny like that. Okay, but to 2 sig figs, it's 0.70. So therefore, yes, both of these are in fact satisfied. Now this last one was, I warned you that question 2 from the last test would come back here. And so in this one, we have the molecular weight of component D given, and the mass flow rate of component D is what we're trying to find out. So it's 120 part per million D, okay, at 80 pound moles per hour. So I have 80 pound mole of solution per hour, okay. 120 part per million, that's 120. These are mole fractions, so pound mole of D per 1 million pound moles solution. Okay, so I'm now in the pound moles of D game. Okay, but it wanted in pound mass per hour, not pound mole, so that's where I use the molecular weight. So the molecular weight is 80, and I'm sorry that I used the same value twice there. I wasn't thinking. Okay, so 80. The units on this are grams per gram mole, kilograms per kilomole, or pounds mass per pound mole. In this case, I want pound mass of D per pound mole of D. So pound moles of D cancel. I'm left with pound mass of D per hour. And so the answer is 0.768 pound mass per hour.